No one remembered her name. Yet every bomber that crossed the channel carried her signature, hidden inside the metal, measured in thousandths of an inch. Her work never appeared in headlines. It existed in margins, in pencil, beneath the heading revised under Specification 43B-17F tail 04. No medal, no citation, only numbers. And yet, those numbers kept aircraft intact when the sky itself tried to tear them apart. For decades after the war, crews remembered the Memphis Belle, the first flying fortress to complete 25 missions over occupied Europe. But none of them knew that part of its strength traced back to one calculation made quietly in a sealed Boeing drafting room. Boeing Plant 2. Seattle, Washington, March 1942, 6:18 a.m. Temperature 6 degrees Celsius. Outside, steady rain blurred the Duwamish River. Inside, the air vibrated with the continuous percussion of rivet guns. Rows of fuselage sections stretched end to end across the hangar floor. Aluminum cylinders suspended on steel jigs under fluorescent glare. Overhead cranes moved wing panels through haze that smelled of solvent, graphite grease, and burnt oil. The floor trembled under hydraulic presses, each movement timed to production flow charts pinned above the supervisor's desk. Every 57 minutes, one new airframe segment advanced toward assembly. At night, the factory became another landscape, an illuminated cavern of heat and vibration. Welding arcs flashed blue-white across the rafters. Sparks fell like rain over scaffolds. The smell was constant: acetone, machine oil, ozone, iron dust. Air pressure changed each time the hangar doors opened, causing blueprints to lift slightly from their boards. Ventilation ducts rattled against steel beams. The combined sound of riveters, grinders, and cranes formed a mechanical roar measured at 98 decibels. Ear protection was minimal. Communication occurred through hand signals, chalk marks, and procedural notes taped to the bulkhead. Civil Aeronautics Authority inspectors walked the aisles twice each day. They checked torque readings, rivet pitch, and skin curvature tolerances. Inspection Bulletin, CAA 23, mandated full verification of structural assemblies against the master blueprints. Each print was classified under War Department Order 57B-17. Confidential, restricted data. Do not remove from premises. Violations were prosecutable under the Espionage Act. Armed guards patrolled the exits. No notes left the building. The factory operated around the clock. 3 shifts cycled continuously: 4 a.m. to noon, noon to 8 p.m., 8 p.m. to 4 a.m. The lights never dimmed. Even at 2 a.m., the air shimmered with heat from welding bays. Compressed air lines hissed under pressure. Hydraulic presses echoed through concrete floors. The oxygen content near the riveting stations dropped below 18%. Workers moved methodically, trained through emergency WPA programs. The Works Progress Administration had established courses for women technicians, drafting, materials science, stress analysis. Their textbooks contained diagrams of trusses and beams, but no mention of war. Now those lessons applied to aircraft production. By early 1942, more than 40% of Boeing's engineering staff were women, many classified as temporary. They worked 12-hour shifts, with 30-minute meal breaks. Precision was not optional. Among them, one name appeared repeatedly on internal memos: E.C. Whitmore. Age 24. Graduate of the University of Washington, Department of Mechanical and Aeronautical Engineering. Employed as Junior Structural Analyst, Airframe Section 2 Billions. Her role: vibration, harmonics. She studied how repeating stress cycles traveled through the fuselage skin, amplifying at specific frequencies. Her desk held a slide rule, vernier calipers, and fatigue data from the National Advisory Committee for Aeronautics. Her handwriting was mechanical, numbers aligned as if printed. The B-17 program demanded quantity, speed over refinement. The Army Air Forces required bombers faster than the engineers could improve them. Each redesign threatened delivery quotas, but inspection reports from early flights described cracks forming near the rear. Fuselage bulkhead, small fissures visible only when paint was stripped away. Most engineers called them non-critical. Whitmore disagreed. She recalculated the natural frequency of the tailplane. At cruise, engine speed was 1,750 revolutions per minute. That vibration aligned with the second harmonic of the tail structure. If amplitude reached threshold, a standing wave would form along the O. Skin panels, undetectable on the ground, catastrophic in the air. At 25,000 feet, with metal embrittled by cold, it would cause a progressive fracture from rivet to rivet. She replotted the load curves by hand. No computers, no calculators, only a QFL and ESSA 4081 slide rule and logarithmic tables. Each data point converted from deflection to stress per square inch, then plotted along a Wöhler curve, the standard fatigue diagram developed in 1860s Germany. She referenced NACA Technical Note 873, fatigue strength of duralumin under repeated stress. Her notes filled 2 pages, stress amplitude versus cycles to failure. The margin showed Goodman correction applied for mean stress. Result: 4 fuselage frames exceeded allowable limits. All corresponded to the junction between the vertical fin and the upper longerons. Her proposal was precise. Add doubler plate, 0.06 4-inch 24 stones alclad, riveted 8-32 pattern, span 22 inches. Weight increase 32 pounds. Compensate by taper milling skin forward of frame 9. Net difference plus 0.2 pounds, within tolerance. Supervisor F.R. Talbot reviewed the drawing, stamped deferred, and filed it under pending revisions. Production schedules could not slow for theoretical resonance. But by June 1942, similar reports arrived from the Wichita and Vega plants. Pilots described rhythmic vibration through the rudder pedals at high climb power. Inspections revealed cracks at the same coordinates Whitmore had identified. The deferred file returned to her desk. Handwritten in pencil across the margin, test per recommendation ECW, Plant 2 Experimental Lab. Test article B-17F to 3BO entered the static rig April 9, 1942. Technicians bolted the fuselage section onto a steel frame fitted with eccentric cam drives that replicated engine vibration. Instrumentation: 6 bonded resistance strain gauges, calibrated using a Wheatstone bridge network, carbon paper oscillographs. Tracing voltage variation onto moving graph paper. 2 displacement transducers reading 0.25 inch amplitude. Thermocouples measured skin temperature at 18 degrees Celsius baseline. Calibration involved zero load readings recorded over 5 minutes to eliminate electrical drift. Vibration frequency increased incrementally until resonance reached. At 72% simulated engine speed, tail amplitude measured 0.12 inch. After Whitmore's modification, 0.04, 2/3 reduction. The datasheet read, resonance damped 66%, no panel separation. Recommendation, approve for production. Engineering Order 1432, issued April 17, 1942. Implementation began with fuselage serial 41 to 24,392. That airframe would later receive the name Memphis Belle. By summer, the factory reached maximum output. Floodlights made night indistinguishable from day. Welding arcs illuminated catwalks. Metal dust coated the windows in gray film. Each finished fuselage advanced toward the assembly dock on a chain conveyor, guided by chalk lines painted on the floor. Every shift produced one completed airframe. Civil Aeronautics Authority inspectors checked 3 units per week, signing off on torque values and material batch numbers. Blueprints never left the building. Pages were logged out and returned under guard. Technical secrecy matched any weapons program. War Department Bulletin 202A restricted use of strategic materials to combat aircraft only. Aluminum stockpiles measured daily. Rejected panels were melted and recast. The smell of hot alclad filled the air. Plant humidity kept within limits by ceiling fans rotating above the draftsman. The environment remained constant. Heat, noise, precision. Spring 1943. Bassingbourn Airfield, England. Altitude 8,000 feet. Formation of 12 B-17’s 91 Stones bomb group. Objective Wilhelmshaven. Airspeed 155 knots. Outside temperature 35 degrees Celsius. Engines turning 2,100 revolutions per minute. Flak bursts at 21,000 feet. Fragments perforated the stabilizer. 94 holes recorded after landing. The tail held. Reinforcement performed as calculated. No one aboard the Memphis Belle knew the reason. Bremen Raid, April 17th, 1943. 78 fortresses departed. 10 lost. Memphis Belle returned with dented fuselage and jammed elevator trim. Tail integrity unchanged. Recorded stress 2.5 grams during evasive maneuver. Within safe limit. Hamburg mission, July 25. Altitude 23,000 feet. Temperature 45 degrees Celsius. Crosswinds 50 knots. Continuous turbulence. Flight duration 9 hours, 37 minutes. Inspection report. No distortion to reinforced fin. Saint Nazaire attack, August 1943. Flak density 200 bursts per minute. 2 hits near tail. Cracks non-propagating. Structure stable. Regensburg mission. August 17. Aircraft from other groups suffered fin failures. The Belle returned without damage. Ground crews at Bassingbourn conducted post-mission fluorescent inspections. Zinc chromate dye sprayed across rivets. Under ultraviolet light, older models revealed fractures. The reinforced series did not. Maintenance. Form AAF 505 listed tail failures. None reported. Back in Seattle, Whitmore studied test coupons exposed to temperature gradients. Samples cycled from 60 degrees Celsius to plus 80 degrees Celsius in environmental chambers. She examined micro cracks under metallographic microscopes at 400x magnification. Results plotted against Goodman diagrams showed fatigue strength retention above 90% at extremes. Each measurement entered on Form X37T. The specimen, with reinforcement, endured 2.3 million stress cycles before rupture. Other teams faced wing spar buckling and nacelle fatigue. But Whitmore's method proved a principle. Geometry could replace weight as strength. Army Air Force's Engineering Division cross-checked data through Langley Field's structural lab. Correlation within 0.9% of prediction. Confidence high. Standard adopted. By late 1943, Plant 2 produced 16 bombers per day. Each aircraft contained 293,000 parts and 230 miles of wire. Inspection teams spent 4 hours per unit. Checklist line 17 degrees Celsius red, doubler, fin root, verify rivets tight. Serial numbers passed Whitmore's window hour after hour. Each one carried her reinforcement under layers of primer and paint. Statistical summaries confirmed results. In 1942, tail fatigue failures 3 per 1,000 flight hours. In 1943, less than 1. Improvement recorded. Name omitted. When the Memphis Belle returned to the United States in June 1943, newsreel crews captured the arrival. The film showed smiling airmen and officers beneath sunlight. Behind them, the tailplane reflected light off Whitmore's plate. Factory stamp 2B. Inspection mark W17. The night shift continued under blackout curtains. Mercury lamps cast hard shadows across machines. Air vibrated from compressors. Paper edges lifted in drafts. Whitmore adjusted oscillograph feed rates, ensuring recording curves remained clean. She computed damping ratios by hand, using logarithmic decrements between peaks. Numbers only. At 2:43 a.m., she filed the final test sheet. Annotation: cycle complete. No failure. By 1944, she proposed elliptical lightning holes in tail ribs to reduce stress concentration. Weight reduction 8 pounds. Vibration amplitude down 10%. Adopted for B-17’s series. Credit line. Per prior spec. Between August 1943 and May 1945, 8th Air Force. Maintenance logs showed 42% reduction in tail replacements. Report summary. Improved metallurgy. No further detail. August 14th, 1945. 5J Day. Whistles echoed through Seattle. Plant 2 machinery stopped. Silence returned for the first time in 4 years. Within weeks, production ended. Half the workforce released. Whitmore remained through final inspection in February 1946. Personnel record. Resigned. Civil sector. The Memphis Belle, stored at Altus Field, later exhibited as symbol of endurance. Visitors saw paint, nose art, gun turrets. None saw the internal plate. Maintenance log. Doubler per EO 1,432. Serviceable. Post-war evaluation began quietly. The Bureau of Aeronautics requested Boeing's fatigue data for comparison with new pressure cabin bombers. From 1945 through 1947, engineers at Langley Memorial Aeronautical Laboratory examined B-17 fuselage fragments to study cyclic stress propagation. Sections removed from reinforced aircraft displayed clean load transfer. Fracture lines terminated precisely along the edges of Whitmore's doubler plate. The pattern confirmed that stress had been absorbed and dispersed before damage could advance. Langley's report, Technical Memorandum 1123, cited reduction of local resonance by geometrical redistribution. No individual credited. Only the specification number appeared. The lessons transferred directly to the B-29 Superfortress. Its pressurized cabin required airtight seams and thicker skin panels. Structural engineers adapted Whitmore's method to circular frames, inserting reinforcement strips along windows and access ports. Early pressure tests reached 8.7% psi differential. Without reinforcement, rivet rows failed at 6.9. The modification extended service life by a factor of 2. Her geometry had evolved into policy. By 1947, Boeing engineers were developing the B-50, a redesigned derivative of the Superfortress. Stress diagrams still contained shaded rectangles drawn where reinforcement plates sat hidden behind the outer skin. Each one traced back to the B-17 data of 1942. The rule was simple. Distribute vibration. Control amplitude. Avoid harmonic alignment. It became standard in every heavy bomber produced afterward. Langley researchers advanced fatigue science through systematic testing. Rotating beam machines, torsion bars, and cyclic loading rigs measured endurance limits. Results plotted on Goodman diagrams, the same method Whitmore used by hand. The mathematical relationship between mean stress and alternating stress defined design philosophy for the next decade. By 1950, these findings formalized into military standard Mille 8, 1866, airframe fatigue analysis and testing. The wording mirrored her own test notes. Allowable cyclic load shall include harmonic interference margin no less than 15%. Her principle had become regulation. As piston engines gave way to jets, the problem changed scale but not form. The B-47 and B-52 encountered new resonance from swept-wing flexure. Engineers reviewed historical data from the B-17 tail section to understand fatigue life. They discovered the same mathematical curve repeated across eras. The geometry still held. By then, Whitmore's name had vanished from company files. Personnel rosters from 1942 to 1946 listed her as employee 217 B2 to 143. No photograph survived. Payroll terminated March 1946. No forwarding address. Only engineering order numbers remained. Blueprint 31,121 F11, a carried annotation. Reinforce per ECW mod. Initials faded to faint graphite. Through the 1950s, fatigue research intensified. Jet transports experienced metal creep at high temperature. Structural labs revisited every wartime design to establish baseline endurance. Old B-17 components provided the data foundation. The Air Force Materials Laboratory at Wright-Patterson analyzed fuselage frames with microscopes capable of 800x magnification. They observed microcracks initiating at rivet holes but terminating at doubler interfaces, exactly as Whitmore's formula predicted. A 1956 report summarized the phenomenon as stress arrest by stiffness gradient. Her approach predated the terminology by 14 years. Throughout these developments, her original mathematics survived intact. A 1958 fatigue handbook reproduced her load curves, unlabeled, within an appendix. The diagram's axes, stress amplitude versus logarithmic cycles, matched her notation perfectly. Decades later, computer analysis verified her predicted endurance limit within 0.8% of experimental results. She had calculated with pencil and slide rule what machines later confirmed with silicon. The Memphis Belle itself aged in silence. Stored in hangars, repainted, stripped, restored. Its surface recorded layers of maintenance, each concealing the hidden plate. In 1978, engineers from the Air Force Museum initiated preservation work. When they disassembled the tail assembly, they discovered rivet rows that did not match the early 1942 production drawings. Each rivet exactly spaced at 1-inch intervals across the upper longeron. Metallurgical analysis revealed 24 cent alclad alloy, 0.64-inch thick. The specification Whitmore had drafted. Tensile strength measured 58,000 psi. Corrosion minimal. The reinforcement had endured unaltered for 35 years. They photographed the section under ultraviolet light. A faint imprint appeared inside the metal, W17. No documentation explained the code. It matched inspection marks found on factory test samples from Plant 2. Archival researchers traced the number to airframe section 2 billions. Workstation 17, the same bay where Whitmore had worked. Her signature remained embedded in metal. Restoration technicians reassembled the structure using original rivet tools. They logged the find as unidentified reinforcement per field modification 1942. When questioned, surviving engineers speculated it came from an early vibration study. They could not name its author. In 2008, Boeing archivists began scanning wartime drawings for digital preservation. Among them, microfilm reel 227B-17 contained engineering order 1432 and corresponding test sheets. Page 2 carried the notation analysis by E.C. Whitmore, cross-reference with plant directories, confirmed employment dates, project code, and inspection mark W17. The connection between blueprint and airframe re-established after 66 years. Digital analysts compared her 1942 calculations to later test data from jet aircraft. Stress frequency curves aligned almost exactly. Her damping ratio, derived manually, equaled 0.043, identical to computer simulations conducted with finite element models in 2010. Her geometry had become timeless mathematics. Meanwhile, historians documented the broader industrial context. Boeing Plant 2 had spanned nearly 1 million square feet. It consumed electricity sufficient for a city of 50,000. Each night, welding arcs lit the riverbank through blackout curtains. The air carried a fine dust of aluminum oxide. Ventilation fans hummed without pause. Civil aeronautics authority inspectors verified compliance with Bulletin 41-231. Every rivet torque, every alloy certificate, every fuselage alignment. Blueprints remained locked in steel cabinets under armed guard. Drafting paper bore red stamps, confidential, restricted by War Department order. Not a single drawing left the premises without authorization. The plant's soundscape persisted in memory. Compressor hum, conveyor clatter, hammer rhythm. Temperature fluctuated between 28 and 36 degrees Celsius near furnaces. Ozone mixed with acetone. Workers wore cotton masks, blackened by dust. Pressure gauges hissed as airlines bled. Under those conditions, Whitmore calculated resonance curves. No ornament, no distraction, only mathematics, precise and absolute. Her vibration tests had used equipment primitive by later standards. Bonded strain gauges connected through copper wiring to galvanometers. Pen traces burned onto carbon paper by electrical heat. Each oscillation recorded as a thin black curve. Calibration required zero drift verification every 20 minutes. Temperature correction applied by resistor compensation. The process took hours for a few seconds of accurate data. She translated the amplitude decay between peaks into damping coefficients by logarithmic subtraction. Handwritten, systematic, correct. Material tests, under varying temperature, confirmed behavior at altitude. Specimens chilled with dry ice reached 60 degrees Celsius. Aluminum hardened, became brittle, but retained 90% yield strength. She documented every microfracture visible through a metallographic microscope. Under 400x magnification, grains appeared elongated. Fracture angles measured precisely at 38 degrees to rolling direction. The reinforced specimen displayed energy dispersion rather than rupture. That pattern later became textbook material for aircraft fatigue studies. Operational records supported the theory. Between 1942 and 1943, aircraft without reinforcement showed early fatigue failures near tail section frames. After the modification, failures virtually disappeared. Flight logs from the 91 Stones bomb group listed no catastrophic structural losses after mid-1943. The improvement corresponded directly to her engineering order. Combat environments validated the numbers further. The Hamburg mission of July 25, 1943, subjected bombers to sustained turbulence. Airspeed 152 knots. Altitude 23,000 feet. Outside, 45 degrees Celsius. Wind shear produced roll angles up to 5 degrees. Instrumentation recorded vibration amplitudes up to 0.07 inch. Whitmore's reinforcement held the resonance below 0.04, the predicted safe limit. Saint-Nazaire, August 1943, heavy flak concentration, shell bursts 200 per minute. Tail sections, peppered with fragments. Post-flight dye inspection revealed no fatigue cracks. Regensburg, August 17. Aircraft endured high-altitude compression waves from exploding shells. The Memphis Belle sustained 2.7 grams acceleration. No deformation recorded. All within specification. Maintenance officers compiled comparative statistics. Early B-17 models averaged one tail replacement per 600 flight hours. Reinforced B-17 F and G models extended average life beyond 1,400 hours. Engineering Division summarized: design improvement effective, origin unrecorded. In truth, the origin sat in a drafting room at Plant 2. Post-war technical literature acknowledged the phenomenon indirectly. NACA Report 1381, 1958, on high cycle. Fatigue in riveted joints cited experimental data matching her curves without attribution. The science had transcended its source. Her equations formed invisible infrastructure of modern airframe design. By the 1960s, as aerospace entered the jet age, the fundamentals remained unchanged. Resonance control, load redistribution, harmonic isolation, all drawn from the same logic. Boeing engineers developing the 707 reviewed wartime archives for historical fatigue data. In microfilm files, they found the familiar annotation, ECW mod. It reappeared on graphs, comparing test results for the 77's pressurized fuselage. Even in a new generation of aircraft, her geometry provided baseline safety factors. Decades later, restoration of the Memphis Belle resumed with modern tools. Technicians dismantled the empennage for ultrasonic inspection. They mapped rivet spacing with laser measurement. Distances averaged exactly 1 inch center to center, variation less than 0.0. Alloy composition confirmed through spectrographic analysis: aluminum 4.5% copper, 1.5% magnesium, trace manganese, hardness 115, Brinell, consistent with 1942 production. Corrosion negligible. The reinforcement had survived exposure, humidity, and time without measurable degradation. When restorers reattached panels, they logged observations in digital archive. One notation read, "Unidentified reinforcement, tail station 11 AW17 mark." Historians correlated the code with the rediscovered engineering order. The file matched. Her presence reappeared after nearly 70 years of anonymity. In 2010, Boeing historians compared Whitmore's 1942 calculations with modern finite element analysis. Stress contour plots mirrored her manual graphs. Deformation, under 2 grams load, measured within 0.5% of her predicted value. Her work prefigured the accuracy of digital simulation. A pencil had equaled a supercomputer. Aerospace design continued evolving, but her principle remained fundamental. No structure is static. Every component vibrates. Strength depends not on thickness, but on geometry and resonance control. That understanding defines all modern aircraft, from jetliners to spacecraft. Her method underlies every fatigue analysis performed today. In archives, her documents endure. Blueprint 31121 F11, are preserved in acid-free storage, graphite lines still legible. Oscillograph, traces scanned to digital format. Her handwriting, angular, concise, unemotional. Numbers aligned vertically, precise to 4 decimals. Between them, the notation, resonance suppressed, verified, no commentary, only fact. Visitors at the Air Force Museum observe the restored Memphis Belle under bright display lights. They see olive, drab paint, mission marks, bullet scars. They rarely notice the extra rivet row beneath the tail fin. Yet, that line of metal carries the logic that changed aircraft design forever. It absorbed vibration that once threatened disintegration. It transformed the bomber from temporary weapon into enduring machine. All because one engineer, unseen, recalculated the harmonics of flight. Records of Boeing Plant 2 now exist only in photographs. The building demolished in 2010, but its echo persists in every fuselage that followed. The mathematics forged there continue in modern aerospace design. Every wing, every tailplane, every pressure cabin built since carries the principle. Whitmore defined, distribute load, isolate resonance, survive repetition. Precision became heritage. No ceremony marked her achievement. No medal, no citation. Only the enduring stability of metal under strain. Her name remains absent from history books, but her numbers remain alive in every aircraft that endures turbulence without failure. The silent correction she drafted in 1942 became a universal law of design. In the archives, light reflects off the faded graphite lines of blueprint, 31,000, 1 and 21 FA. Beside the revision block, a small rectangle outlines the added plate that absorbed unseen energy. Each inspection photo shows the same pattern repeated across decades. Every aircraft built since carries a trace of that geometry, scaled, refined, uncredited. The museum's technical report describes the reinforcement as early example of harmonic control through distributed stiffness. The term is modern, but the act was hers. Her logic bridged generations of engineers without any need for recognition. Metal remembered what humans forgot. There was never a ceremony, only the low hum of machinery, the heat of fluorescent lamps, the smell of graphite and oil. A pencil moved across paper, and the shape of endurance appeared. That single correction altered the fatigue history of aviation. Every oscillation of every airframe owes something to that line of graphite drawn in 1942. The blueprint corner bore her initials, faded now, yet every Memphis Belle that followed carried her correction in silence.